Hello, I'm Youngbom Kim from Dongguk University DTM Lab. Today I'm going to review a paper titled Graph Self-Supervised Learning, a Survey. It provides a comprehensive review of self-supervised learning methods for graph structures data. This slide shows the bibliographic information of the paper. This paper was published in IEEE Transactions on Knowledge and Data Engineering. The main keywords include self-supervised learning, graph analytics, graph representation, and graph neural networks. The paper highlights three key points. First, most graph representation learning methods rely heavily on label data, which is scarce and expensive. Second, graph self-supervised learning leverages abundant unlabeled data through well-designed pretext tests. Third, unlike SSL in Vision or NLP, graph SSL must handle complex topological dependencies and non-Euclidean structures. Here are the contents of today's review. Now I'll introduce the research background. Graph structures data are widely used across many domains, and most graph deep learning studies rely on supervised or semi-supervised learning with manually labeled data. However, heavy dependence on labels leads to high annotation costs, limited generalization under scarce data, and vulnerability to adversarial settings. To address this issue, self-supervised learning designs pretext tests to learn representations directly from unlabeled data, reducing reliance on manual labels. SSL has already achieved strong success in computer vision and natural language processing. However, directly applying SSL techniques from CV or NLP to graphs is challenging because graph data exist in irregular, non-Euclidean spaces and contain complex topological dependencies between nodes. With the rapid growth of graph SSL research, a unified framework and systematic taxonomy are needed. Therefore, the survey proposes an encoder-decoder framework and categorized existing methods into generalization-based, auxiliary proposed-based, contrast-based, and hybrid approaches. This slide introduces several basic definitions used in the paper. First, manual labels and pseudo-labels. Manual labels are created by humans, so they require expert knowledge and high cost. Pseudo-labels are generated automatically from data itself. In graph self-supervised learning, these pseudo-labels are usually produced through pretest tests. Next, downstream task and pretest task. Downstream tasks such as node classification or graph classification are used to evaluate learned representations and usually require labeled data. Pretest tasks are auxiliary tasks designed to create supervision signals from unlabeled data. For example, reconstructing graph structure. By solving pretest tasks, models can learn useful and transferable representations. Finally, supervised, unsupervised, and self-supervised learning. Supervised learning used manual labels. Unsupervised learning does not use labels. Self-supervised learning generates supervision signals directly from the data itself. This slide explains basic graph concepts used in the paper. First, a plane graph. A graph consists of nodes and edges. Nodes represent objects and edges represent relationships between them. The connections between nodes are described by an adjacency structure. Next, an attributed graph. In many real-world cases, nodes and edges also have feature information. These features describe properties of nodes such as attributes or text information. So an attributed graph includes nodes, edges, and their features. Finally, graph neural networks. Graph neural networks are used to transform low node features into meaningful node representations by using graph connectivity. A readout function can then combine node representations into graph-level representation. This slide explains the unified framework and the taxonomy of graph self-supervised learning. First, the unified framework. Graph SSL is described using an encoder-decoder structure. The encoder learns low-dimensional node representations from the input graph. Then the pretext decoder uses these representations to solve self-supervised tasks. The encoder is trained by minimizing a loss generated from the pre-task task. After this stage, the trained encoder can be reused for downstream tasks by attaching a new decoder trained with labeled data. So the framework clearly separates two stages: self-supervised representation learning and supervised downstream task learning. Next, the taxonomy. Based on how pretest tasks are designed, graph self-supervised learning methods are divided into four main categories. The following slides will explain these categories in detail. This slide introduces generation-based methods. These methods learn representations by reconstructing graph data. In other words, the model tries to recover the original graph information. There are two main types. One is feature reconstruction, where the model reconstructs node features. The other is structure reconstruction, where the model reconstructs graph connections. The objective is simple. The model minimizes the difference between the reconstruct graph data and the original data, so the decoder and training objective are relatively straightforward. However, choosing meaningful reconstruction targets often requires careful design and some domain knowledge. The figure below shows examples of feature masking and edge masking used in generation-based methods. These slides introduce auxiliary property-based methods and contrast-based methods. First, auxiliary property-based methods. These methods create supervision signals from graph properties. For example, regression-based methods predict numerical properties like node degree. Classification-based methods generate pseudo-labels such as cluster indices. The loss function depends on the property type. If it is numerical, regression loss is used. If it is categorical, classification loss is used. The decoder and objective design are relatively simple. However, choosing meaningful graph properties often depends on domain knowledge. Next, contrast-based methods. These methods learn representations by maximizing agreements between different views of the same graph. Two augmented versions of the same graph are generated. The model then tries to make representations of positive pairs similar. There are two main types: same-scale contrast such as node-to-node or node graph-to-graph, and cross-scale contrast such as node-to-graph. Contrast-based methods are flexible and usually show strong performance, but they require careful design of augmentation strategies and loss functions. This slide explains hybrid methods and different training schemas in graph self-supervised learning. First, hybrid methods. Hybrid methods combine two or more pre-task tasks. For example, reconstruction can be combined with contrastive learning. By combining multiple tasks, the model can benefit from complementary supervision signals. However, it requires careful balancing of different training objectives. Next, the training schemas. Graph SSL training strategies are divided into three types based on how pre-task and downstream tasks are combined. The first is training and fine-tuning. The encoder is first trained using pre-task tasks, then it is fine-tuned with labeled downstream tasks. The pre-training and fine-tuning datasets may be the same or different. The second is joint learning. The encoder is trained simultaneously with both pre-task and downstream tasks. The total loss combines self-supervised loss and supervised loss. This works like a multi-task learning framework. The third is unsupervised representation learning. The encoder is trained only with pre-task tasks and then frozen. A downstream classifier is trained separately. This setting is more challenging because the encoder does not receive downstream supervision. The figures at the top briefly summarize the three training schemas introduced earlier. Figure 2 shows pre-training and fine-tuning. Figure 3 illustrates joint learning, and Figure 4 presents unsupervised representation learning. These figures visually compare how pre-test tasks and downstream tasks are combined in each settings. Below, the slides introduce the taxonomy of downstream tasks. Downstream tasks are categorized based on prediction scale. Node-level tasks focus on predicting properties of individual nodes. Link-level tasks predict relationships between pairs of nodes. Graph-level tasks predict properties of entire graphs. This classification helps evaluate how well-learned representations perform at different levels of prediction. This slide explains feature generation and structure generation methods. First, feature generation. The idea is to reconstruct nodes or edge features from the original or perturbed graph. Common strategies include feature masking or adding noise to features. The model then tries to recover the original features. This approach helps capture node-level semantic information. However, it may struggle when features are extremely high-dimensional or very sparse. Next, structure generation. Instead of reconstructing features, this method reconstructs the graph structure itself. The model predicts whether two nodes are connected or not. Sometimes it predicts a full adjacency structure or only masked edges. This approach captures structure dependencies between node pairs, but it can be computationally expensive, especially for large and sparse graphs. This slide explains auxiliary property-based methods in more detail. First, auxiliary property classification. Instead of using manual labels, the model learns from automatically generated discrete pseudo-labels. These pseudo-labels are constructed from graph properties and optimized using classification laws. There are two common strategies. Clustering-based methods assign nodes to cluster and treat them as pseudo-classes. Pair relation-based methods define pseudo-labels based on relationships between node pairs such as distance or centrality. This approach provides flexible supervision signals, but its performance depends on how well the pseudo-labels are constructed. Next, auxiliary property regression. Here the model predicts continuous graph properties instead of discrete labels. Common targets include node degree, distance to clusters, or similarity between node pairs. These methods are optimized using regression laws. They provide richer numerical supervision, but continuous properties must be carefully designed. This slide explains graph augmentations and contrastive strategies. First, graph augmentations. Different views of the same graph are generated to create contrastive signals. There are three main types. Attribute augmentations modify node features. Topological augmentations modify graph structure. Hybrid augmentations modify both features and structure. Next, contrastive strategies. Methods are divided into same-scale and cross-scale contrast. Same-scale contrast compares representations at the same level, such as node-to-node or graph-to-graph. Cross-scale contrast compares representations at different levels, such as node-to-graph or subgraph-to-graph. Finally, contrastive learning objectives. Contrastive learning is often based on mutual information estimation. Common objectives include info NCE loss, Jensen-Shannon-based losses, and negative-free approaches such as BYOL. This slide explains how different methods are integrated. First, generative and contrastive integration. This approach combines reconstruction tasks with contrastive learning objectives. The generative task helps preserve structure or feature consistency. The contrastive task helps improve discriminative representation learning. The overall object is usually a weighted combination of reconstruction loss and contrastive loss. By combining them, the model can capture both local structure information and global semantic relationships. However, balancing multiple objectives is important to avoid unstable training. Next, multitask contrast and auxiliary property learning. Here, multiple contrast objectives are integrated, or constructive learning is combined with auxiliary property prediction. The model can learn from different levels, such as node level and graph level at the same time. Auxiliary property tests provide additional supervision signals, which improve generalization and transferability, but these approaches increase computational costs and require careful tuning. This slide presents node classification performance and empirical resources. First, node classification performance. Graph SSL methods are evaluated on standard benchmarks such as Cora, under both transductive and inductive settings. The results shows that contrast-based and hybrid methods generally achieve stronger performance than early generative or random walk-based approaches. In addition, methods that combine self-supervision with partial label access tend to outperform purely unsupervised methods. This suggests that combining self-supervision with downstream supervision can further improve performance. The table on the right summarizes the experimental research across different methods and datasets. Next, next, empirical resources. The paper also provides benchmark datasets for both node-level and graph-level tasks. In addition, open-source implementations of many survey methods are collected to support reproducibility and future research. This slide presents practical applications and conclusions. First, practical applications. Graph self-supervised learning has been applied to recommender system, anomaly detection, and chemistry. It is especially used in environments where label data is limited. For example, it helps with call start recommendation, anomaly pattern detection, and molecular property prediction without heavy reliance on manual labels. These examples show that Graph SSL is well suited for real-world scenarios where graph data is abundant but labels are scarce. Next, the conclusions. This survey systematically categorized graph self-supervised learning into generation-based, auxiliary property-based, contrast-based, and hybrid methods under a unified framework. It also provides mathematical formulations, empirical comparisons, and originalized research resources to clarify the current landscape. Although grep SSL shows strong empirical performance, challenges remain in theoretical understanding, robustness, augmentation design, and multitask integration. Future research should strengthen theoretical foundations and extend grep SSL to more complex graph types and broader applications. Thank you for listening my paper review.